Okay, and what I would like to do is go back to the beginning of the course and review the parts of it and try and help create a set of summary notes that takes the material we've covered over the last 12 weeks or so and bring it into a single notebook. Now, what I have up on the screen that you should be able to see, I'm sharing, is a document that I've called Lecture 01 to 19 Combined. Now, I haven't shared and posted this. All I did is I just took all of the lectures we've done and I merged them into one giant Jupyter notebook. And what I'd like to do collectively as a group is go through the lectures and use that as a motivation to review what we've done. And once we've cleaned this up, I'll post this and share it with you so you've got sort of a combined version of what everything in the course is. As we go through the lectures in review, if there are things you want to slow down and discuss, now's the time. If you want to ask questions like, will this be on the exam? That's a great question. I'm going to try and help sort of review the course in this way. Now, one of the things that the course did is it introduced some topics in stages. So, for example, we began the course in Lecture 1 discussing this equation. That's a decay equation. We modeled it on the radioactive decay of uranium-238, and we used it to introduce the idea of solving a problem numerically. There's things that we did in that first lecture that we would do slightly differently now that we've reached the end of the course. So one of the things I'm going to do today is sort of rewrite that lecture in the notation and the style that we've come to once we've got to the end of the course, cleaning it up a lot, as I said. So what we'll do is I'd like to go through the lectures, and so I've got the content of them, and with your participation, let's reduce these lectures down to a set of summary notes so that it really highlights the parts of the course, if nothing else, that I think is important and am forming a final exam around. As I said, so I haven't posted this yet because we're going to shrink it down. It's a fairly sizable notebook that I'm going to just end up deleting large fractions of all the way through. As I said, it's really helpful as we go through this if I can have your feedback. And so what I'm going to get you to do is turn off some of those mics. I see a whole bunch of people with their mics muted. Go ahead, unmute those. If you're like, well, I don't have a microphone and I want to ask a question, the computer that Kyle is sitting next to has a microphone associated with it. Kyle, you're more than welcome to unmute your microphone and invite 2 or 3 students who don't have that kind of technology just to sit where you're sitting. This is sort of what we would do if I was in the room. I don't need to see your faces. I don't need video cameras, though you're welcome to if you want. But your voice is really helpful to hear what's going on. So again, I'm going to invite you to unmute your mic to ask questions or point out things. Okay, so here we go. So what I've done is I've just taken the 19 lectures we've given in this course and combined them into one notebook. There's a lot of material that gets repeated all the way through. So bringing it all together, here is all of the packages that we've been importing throughout the class. Hopefully at this point, you're recognizing some of these packages. NumPy is for numerical Python. Pandas is how we're organizing data. SymPy is for symbolic mathematics. ODEInt is a pre-packaged ODE solver. Matplotlib is a plotting package. TQDM is something we occasionally used when a code ran a very long time and we wanted a progress bar. And then we did something with some interactive things. You'll notice what's not in there. Nothing on 3D plots. 3D plots is a neat sort of idea, but I won't be putting anything on 3-dimensional plotting on the final exam. And there's a few other routines in terms of SciPy optimize that we may want to have in there, because I think we talked about that several times. So I'll add that in. Optimize, import, curve, fit. I think those are all the packages that we ended up talking about in this course. So I just grouped them together, and then I've gone through all of the 19 lectures and just removed them to clean up the code. The second thing I'll remind you of is we did start the class off with sort of an introduction to Python. I'm not sure how many people went through this, but this was sort of the basics of the language. And you'll notice at the end of some, not all, of the lectures, I've been giving suggested textbook readings. Now, I don't need you to go off and read the textbook, but if you want to, there's a link. This is basically what we've covered in the course, these sections or chapters of it. I said I just went through and pulled this all up together as something. I don't think you need to go to this book, but if there is a part of the course where you're like, yeah, this isn't making any sense, there is a textbook, and it may be worth your while to read a few of the pages from that. So I pulled that information out. Okay, so let's go back to the beginning. We started by looking at how we're going to do computer simulations in physics, and I motivated the problem with a 1 decay thing. So here is an example of an ordinary differential equation. This is the kind of thing we've been solving throughout the course. We can solve problems like this symbolically or numerically. Symbolically, this would be SymPy. So the way we solve that is we introduce the symbols involved in the problem. So N and T and K. You need some sort of initial condition to be able to solve anything. So I'm going to define those as symbols, set them up as a system of equations, and then solve it. So here's sort of the basic use of SymPy. The idea is we have to have symbols. We can do things like forming equations, substituting in variables, and doing things like either .solve or .desolve to be able to work with it. Later on in the course, we spend 2 lectures talking about SymPy in more detail, but that's the basic idea. It gives us something that we can compare to. So let's just take that expression right now as a thing and practice our plotting, right? So this is something that we may want to solve or to plot. If we want to plot this, what we need to do is we need to have some idea of time, right? Time's going to have to get advanced throughout this system. And then the way we're going to plot it is we're going to plot this thing for various values of time, and we're going to connect all the dots. Numerically, what we do is we start off at some initial point like n0, and then iterate through time using some numerical method. So when we did the class originally, we had some sort of structure here on how all this worked. And what I want to do now is use the patterns that we've been developing later on in the course to sort of go back to lecture 1 and show you how you would do it again. Okay, so we have the exact numerical solution. Let's do this. Let's talk about how we would do a numerical solution, right? So the basic idea of the numerical solutions we've been dealing with is it doesn't matter the problem. What we've been talking about is taking any sort of problem and breaking it up into some code, which is the stepper, some code which is a plotter, and some code which is the application, right? That's the basic structure that we've had for any one of these courses. The stepper is the code that's going to actually solve this numerically. We have 1 or more functions which visualize the data, and then something that actually runs it. The word pass is just sort of a default in Python saying it's a nothing, it's a null, it's a non-operation. So that's the basic structure. So how would we go about solving this basic equation using this structure? So how do we use the ideas we've covered in the course to pursue it? Well, the way that I'm going to recommend developing software in this course is you build it up in little steps. So the basic idea is you come up with some sort of structure. Oh, why is that not working? That's no good. Okay. The flow that we've been dealing is we create this stepper type thing.
Dr. Munroe?
Yes, Kayla.
You're missing a colon after app. I think that's why it's
I am missing a colon. Exactly. Yeah. But that's why I'm saying building these things up in general. We're gonna we're gonna have some stepper code, right? That's sort of been the pattern, whatever it happens to be. We're gonna take that stepper code and we're going to step through it as a state of frame. That creates the data. And then we're going to plot it, right? That's the basic structure of all these programs. So for this to work, plot has to take in some data and it has to produce a picture, right? So let's just start framing up a basic structure. Well, in this particular problem, I'm plotting data for n versus data of t. I might need to have some labels. Right, that's pretty standard all the way through. And I need some stepper code, something that's going to iterate through the whole model, right? So there's a couple of ways we've set this up. We set it up as a generic stepper, but just for this sort of basic problem, we need some way of encoding the solution. Well, we know the solution starts off at some initial state, right? So that all of these programs, they've got some idea of an initial time and an initial value, right? That's sort of an important aspect of all these problems. The problem starts off at some initial time, and it starts off with some initial amount of data, right? So let's talk with 10 units. That's sort of the basic idea. To step through these things, what we do is we go through a loop, and that loop occurs until the program ends. It's just going to do the same thing again and again and again until it ends. Well, what controls the ending? Well, every time through this loop, I'll do it like this, we're adding on to the time. We're adding something called a time step, right? That's the basic structure. So to run these programs, we're going to need some idea of a time step. If we're going to go to some time, we're going to add 1/10 of a second every time we do it. As we iterate through this thing, we can check. If time is bigger than, say, some maximum time, we can break out of the program and stop running it. And that's how we're going to end. So the stepper code has to have something that's going to terminate after a certain amount of time. Okay, almost got the bare bones structure of any of these programs. Every time you go through the loop, we need to pass back something that's going to create the data frame. And so the way that we've been doing this is we've just been yielding back a dictionary. And the way that the dictionary works is you label all of the variables you want to pass back. And that basically hands this piece of data, a current time and a current value of n, back to the stepper. And because of how this idea of yield's working, what data frame is doing is it's running through this thing until it runs out of data. So that's the basic structure of all of our programs. We haven't done much, but we've got the basic functionality. So now it's time to run this all together and see if I've got any mistakes. And I definitely like to just test things to see if they work or not. Let's see if we coded this up correctly. Okay, there we go. That's a fairly decent program. It started off with an initial condition of 10, and because absolutely nothing was happening, it got to the end. So all of our programs have this basic structure all the way through. And this is sort of the consistent pattern we're going to try and keep every time. As far as the numerical method goes, we have to take this equation and rewrite it some way so that we can update it. So we can write n in terms of the old value of n. And one of the schemes that we know is Euler's method, right? So let's put in some notes here for ourselves and remember that one of the things we can talk about for a numerical method is this idea of Euler's method. And Euler's method says that if you have a particular value of n, or you want to figure out the next value of n, what you do is you have that equal to the current value of n. Basically, you're just rearranging this thing and recognizing the dn dt is the change in n divided by the change in t. When you take that change in t and move it over the other side, that gives you an algorithm for updating. So it's the old value of n times whatever the derivative is, right, multiplied Oh, I don't need a time sign when doing mathematics. Right, so mathematically, that's Euler's method. Right, this is the derivative, this is the time step. We code that up as follows. We say n is equal to the old value of n plus whatever the derivative is. So we need some constants, minus k times n times dt. Okay, for this code to work, we're going to need a k. So let's just stick in a constant there. I don't know. What's someone's favorite number? 3. Everyone likes 3. I don't know if you like 3, but I like 3. So there we go. And let's just check if what this is now doing. Perfect. Okay. So we've got this basic idea that what we're going to do is we're going to start at 10, and it's going to be k at a certain rate. This particular problem had a known solution. So just to round it off, let's confirm that this basic program is working correctly. We only can do that for solutions that have analytical results. So to do that, let's modify our program just slightly so that instead of plotting the data, it just returns the data back. The advantage here is now we can use that again and manipulate it and do something with it, right? So data itself, of course, is just a table. It's a table of values of t and a value of n. That's all that the data happens to be. If we want to compare this to the exact solution, right? Maybe we'll have a function that says plot exact, right? Plot exact might take the current values of the time, calculate the exact values. Well, the exact values is going to be whatever the first value of n happens to be, right? Because that's just the very first value in the data set. And then we're going to have to multiply that by exp times minus times k times t. For this code to work, it needs to know what the value of k is, right? Somehow we have to keep this value of k into the exact solution. So let's do it like that. And then we can plot it. We can say, okay, plot t and n exact. Okay, so when with those two routines, what we can do, because we have the actual data, we can both plot the data and plot the exact routine, and we should get two curves. Those are the two curves. Just to clean it up a little bit, one of the things whenever we've got multiple curves is we like to use labels. That's the one solution, and the other plotting function we had was here. Label numerical solution. And if we're going to bring this all together, let's put a legend all the way through. So there's the basic structure that we covered in the first lecture. And that's it. So all this other stuff, I'm just going to delete that because it's what we sort of did. But to review, if you want to condense the first lecture down to just a few thoughts, solving a differential equation using Euler's method and this basic template is what I would take away from it. Okay, so let's just talk about that for a moment, because this pattern is something we've seen come up again and again. Is there anything in this code chunk that deserves some conversation? Okay, so that's the basic pattern. So if you got that, we're pretty good. And we're always building up this basic thing, looking for different things. Lecture 2. Lecture 2, we talked about an example of a falling ball. Okay, so falling ball, the equation of motion had to do with the force of gravity being minus mg. So in terms of code, what I'm going to do is I'm just going to clean this up so that you don't need to see as much stuff, and recognize that this base example is Fg equals minus mg. That's an example of a force that might be on a system. In terms of the equations of motion, one of the things that we've always been talking about is Newton's law. And this force can be stuck into Newton's law to give you a second-order differential equation. Now, there's an analytical solution. We could derive that using SymPy, or we could just know it from doing something before. And we want to be able to take our basic pattern and solve this equation, right? One of the ideas is if you don't have a first-order differential equation, but you have a second-order differential equation, you can always rewrite any second-order differential equation into a system of first-order differential equations, right? That's the basic pattern. And the idea here is now is to think about y and v as being the state of the system, and v and minus g being the time derivatives of the state. What we're really doing is we can rewrite each one of those pairs in terms of a for difference approximation, and we get the Euler algorithm. So there's the same text we talked about before, but now we're doing it for two variables all the way through. Okay, this is just some commentary about what we're doing. We're going to iterate through those things. So that's a review of what we covered. And then I've got some specific examples that we covered in lecture on how to solve this. So it's always talking about the idea that to solve a differential equation, we're taking the derivative of something is equal to some right-hand side, and this is Euler's algorithm. We put this question in assignment 1. Okay, so one of the things you may want to do is saying, okay, well, what if this was my system of equations, right? So that's not Euler's method. That's a projectile or a falling object kind of thing. How can we adapt the basic structure of what we've been dealing to solve this problem? Now, I've got the code right here, but let me just sort of redo it here as something to demonstrate where this all comes from. So I'm going to call it simulating free fall. I don't really care that it got adapted from that program. And I'm going to solve that generic problem. So in terms of notes, let's take the equation of motion. That's just this piece right here. And I'm going to copy it down to here so that you really see what the system you're solving is. And let's see if we can reconstruct the basic idea of solving this. But now the trick is with two variables all the way through. The basic structure's there. What we need is, and I'm just going to go back to here, some code that's going to step through it, some code that's going to visualize it, and something to derive the whole thing together. So I'm just going to take that code chunk, a basic pattern, copy and paste it here, and let's modify it so that it works for this system of equations. Well, we don't have n anymore. We have an initial velocity. Maybe it's being dropped from rest. We have some initial position. Let's have it drop from 10 meters up. You still need to initialize y and v. That happens all the time. Every time through the stepper, you're not going to pass back the values of n. We're going to pass back the values of v and y. And we have to update the values of v and y all the way through. Well, with Euler's method, what we do is we say, okay, y is equal to, and we're always looking at this equation right here when we're rearranging that. That's equal to the old value of v plus v times the time step. This guy's equal to plus minus g times the time step, right? So what we have here is this is the derivative. I'll do it for structure so you can sort of see all the parts. There's the derivative all the way through. That's the basic structure. For this particular code, what we want to plot is we want to plot the time versus the position, right? Always label your plots. The basic structure is exactly the same. So once we've got the program run, maybe we can plot it. Okay, I got an error, which is fine. Errors can occur all the way through. The error here Name error, we go to the very end, and it tells us what the error is, and the error is the name G is not defined. So what that's telling us is the variable G, Python as a language doesn't know what G is. You need to somehow define that. There's a number of different ways we can bring in those constants. Not any one of them is wrong versus right. We have seen in the course either defining it externally as a global variable. For variables like G, which aren't changing, this is perfectly fine. That's one way of doing it. Another way of doing it is putting it inside the program as a local variable. That's what we did in the previous example for the decay coefficient. And the third thing we can do is we could pass this into the stepper as a parameter. Now, these equal signs are the defaults, right? It means that if you don't pass them in, it will assume that G equals 9.81. So even though there's no arguments in here, it's as if we put in these values all the way through. So that's another way of introducing parameters like G or K or M or whatever into the problem. So recognizing that there's three ways of doing that, we run the code, and there we go. As a function of time and Y, you get this basic falling structure all the way through. Okay, the rest of this lecture was basically just teaching us a little bit about Python, setting that up. How help works, how to define variables, how to do loops. Okay, there is one thing in this lecture that did come up, is the idea of formatting strings all the way through. Sometimes what we want to do is we want to take a value. Let's say the value is 2, 3, 4, 5. Okay, so there is a variable that has some value. In the Python world, just having it be in the last line gives you, it'll just display it. We can be a bit fancier about that though, if we embed it inside of a string. So if we take a string, what I can do is I can format that string. And what that's going to do is take the value of A and put it inside this set of brackets. Okay, it's formatted. Now this is a string, and a string is something that can be printed out. The reason we use print is because maybe we want to print out something more than once. By default, only the very last value of a cell gets displayed. If you want to display more than one thing, you need to have multiple print statements. So this is printing it out once, printing it twice. What we can do is we can format these things. This is something we've seen. If you want to display this value with only a limited number of significant figures, so 2 decimal places, this is saying format this number with 2 decimal places. Okay, that's what that's doing. And the other notation that we've seen is Python also supports the idea of what are called F strings. In F strings, putting an F in front of it means you don't need to actually say dot format, but now whatever's in front of the colon becomes an expression that we can just evaluate. So you see this is a bit more compact way of writing what we have. And then the other advantage of this is you can actually do some expressions. Right, so that's just some text, but I can actually put anything I want inside this bracket and it'll get evaluated for me. So A equals 1.2345, A equals 1.23, 1.23, 3 times A equals 3.70, right? So this is something we talked about in this lecture. You can control just about anything you look about, but that's basically what we covered. Okay. Then we displayed and compared it to the exact result. I don't think there's anything from here that we need to retain. You could take this example and add in the complete result, but that's just using these sort of ideas. I'm going to just get rid of that for our notes. And these were some examples we did, right? This is basically solving the problem again and again and again, several different ways. Let me summarize for you what these examples were doing. Okay, these examples were basically talking about different ways of writing loops. Okay, so just as a note here, so when you're dealing with while true as an idea, there's something else we could use, and the idea would be you could do something like for, you could say, oh, I'm sorry, the keyboard's not working the way I want it to. We could do something like saying n steps equals 1,000, and then for I in range n steps, which key is it? Oh, there we go. Come on, run this thing. Oh, it's raw. I want markdown. If it's markdown, then I can run it, format it. This notation of the triple backspaces is how you can get code into a markdown cell without having to actually run it. So this lecture also talked about another way of looping through things. Rather than using a while loop and a breakpoint, you could just say, I want to go for 1,000 steps all the way through. Okay, is there anything else from that lecture that we need to talk about? In the chat, it says, is y equals v0 at the stepper? Let me go back to the stepper and make sure I haven't made a mistake. You found a mistake. Y equals v0, v equals y0. That is an error. Y, of course, should equal to y0 to 10 to begin with, not all the way through. So let me fix that. Oh, I got a mistake somewhere in here. Y0 is not defined. Why is y0 not defined? Y0 is equal to 10. D equals T0, Y equals Y0, V equals V0. Okay, let's try that again. Right. Okay, cool. Thank you for cleaning that up. I'll just make a little note here. So for our sort of summary notes, I'll call it string formatting. Okay, so lecture 2 basically solved a following object kind of idea. That's what the point of the lecture was. Again, that basic structure. Okay, lecture number 3 introduced the idea of these basic modules, this idea that we're going to have some sort of solver stepper code and something that's going to display the results or plot the results, and then some application. So this entire lecture was building up this strategy for how this would all work. Okay, so I'm going to take all of that content and reduce it down to just a few short notes. Okay. And this had to all do with better programming structure. Okay, so let's do it this way. Stepper function to iterate through the numerical method. Plot function to display the results. And right? So that's the basic structure, is we're going to have a function which we're going to call a stepper, a function we're going to call a plotter, and a function we're going to call the app all the way through. So all this stuff down here is just that same basic program again and again and again. Just for condensedness, we don't really need any of it. We've covered it all. That's everything we were doing this whole lecture. A lot of this is repetition all the way through. Okay. There was one thing we did talk about in this lecture. This is where we introduced the idea of interactives. Sometimes you want to take a program and manipulate it back and forth. So in terms of what that would look like, well, falling ball interactive, Tmax equals 4. So here's how that kind of interactive program would work. I'll change it a little bit so it doesn't just use, I'll use the labels we had before. We had some stepper, and we had some plotter, okay? And in the notation that we've been dealing with, let's get rid of those entirely, okay? So here's the basic example of how we've done these interactive things. Assuming you have, oh, no, wrong, app. Okay, let's do it like, right? So we have some basic application that what it's returning back is the data, and we can plot that all the way through. To make it interactive, we're going to want to pass into the application a variable like Tmax so that it will change every time we run it. Now, as is, I think this is going to generate an error. And the error is app got an unexpected keyword argument Tmax. Well, because in general, if you want to iterate through things, these apps need to take arguments. So what I'll just do is say Tmax equals, I don't know, 5 as a default. And then I can say Tmax equals Tmax. And I can pass that value down into the stepper. So this is something we've seen before as a pattern. Now that I've got that working, I now can do a basic interactive plot. Okay. What interactive is doing is it's calling this function where Tmax is some number between 0 and 5, but we're controlling the value of Tmax. So here it is, Tmax only goes from 0 to 1. Here Tmax goes from 0 up to 5. It's a way of making it interactive all the way through. But beyond that, there's not much more to this thing here. And I'm going to tell you this thing here.
Dr. Munroe,
Yes, Kayla.
the argument for the falling ball interactive app, could you go back up to it, please?
Yes.
Why is Tmax equal to 4, even though you set the parameters for Tmax for the interactive?
It doesn't need to be equal to anything in particular.
Oh, okay.
It's just a default. The reason we use a default is so if I ran it not interactively, I would get some meaningful result.
Oh, okay. All right, then. Thank you.
The other reason we do it is you'll notice that if you don't provide a default, it's going to choose some number in the range of 0 to 5.
Mm-hmm.
But if I provide the default, I want you to look at that 2 right there.
Yes.
It's going to take that as the starting value.
Oh, okay. Oh, okay.
So there's a bit of control in here. Okay, but here's where I want you to take as a takeaway. Nope. Okay, no. Okay, I'm not going to do anything on interactive on the final exam. Interactive requires a computer to play with for visualizing the data. So we covered it. We used it lots in the course, but it's not going to appear in the final exam one way or the other. Okay, so let's just continue to go. A lot of that lecture was coming up with this structure, but that's what it did. We did some other examples. We talked about bouncing, right? So one of the things we did to complicate the problem was to modify the program so that it handles bouncing, right? So the way that we did that, we had the same basic structure that you've got some numerical algorithm, and then depending on the value of y, we did a bounce, okay? So here is one way of doing a bounce. It says, depending on y, if y happens to be less than some value, then you want to change the velocity. Now, here's an example of a bounce that loses energy. You could have a completely inelastic bounce, the one that did not lose any energy. And when it does bounce, what we're doing is we're looking at how y slips below the x-axis. And so we want to modify it so as if it had bounced and bounced back up. So this is an example of a bounce. So what I'll do is I'll just take this code fragment as a bouncing ball to model a, and I'll call a bounce with energy loss. Use.
Yeah, I got you.
And I'll just leave this as a code fragment. Yeah, I want it to work, right? So this is basically just a little bit of code, right? You need to have some velocity, right? You need to have some value of y. I need to have a loss. Okay, let's say there's a 50% loss, right? So there's some little bit of code. And you can see that after it has bounced, if I wanted to print out, say, v equals v, and print out y equals y, right? So maybe that's something we want to do as a demo. Yeah, we'll do it like this. Before bounce. Yeah. So there you go. And we can clean this up a little bit. Maybe we want to put some, make these so they look like 2 decimal spots. There you go. So this is what a bounce does, right? Inside the loop, depending on some criteria of y, modify the variable so that what was an old v becomes a new v. Oh, actually, I guess it should be going down. There. Before the bounce, it should be heading down. After the bounce, it should be heading back up. Y could have been negative, but we will pretend it's no longer negative. It's as if it had bounced and returned back. And we just flip the sign around. So this code snippet is the basic idea of any type of bounce we've seen in the course. So everything else just becomes examples. This is about iterators and data frames, which we've already covered, and a plotting. Okay, so in terms of this lecture, we talked about bouncing. That was our first time we talked about how something would bounce or change direction. There was an example about falling balls we'll get back to, and then we're on to lecture 4. Okay, so we've covered 3 lectures so far in the course and have the overall structure so far. So we're working at about 15 minutes a lecture to go over and review what the ideas were all the way through. So I'll pause here, and you can sort of see what we've done is we've taken 3 lectures and reduced it down to just a couple pages. How is this working? How is this format of me reviewing the course as a whole going? Is this useful, or should we try something different? This is useful, says Andrew. Thank you. Okay, so we'll keep on pursuing all the way through. As I said, I will share this notebook back with you when we're all done. I'm just taking the whole course and trying to distill it down till it's to its essentials, essentially. Okay, so right. So that's all that we did. I'm going to go through all the assignments in the labs as well. So I'll leave these exercises for now, but we can always come back to it. Okay. In lecture 4, we started talking about more. Oh, hold on. There's a message. I think it'd be useful to have a sample problem from each lecture, like the type of question we could be asked and how to go about solving it. I agree, Cassandra. That is something that I will try and work on to try and formulate a series of potential questions based on all these things. Oh, and Andrew seconded that. Okay, that is on my list of things that I will try and do. Once we've reviewed it, I'll try and come up with a question on what could he ask based on this. Okay, effects of drag resistance. This is the point where we start to formulate this idea that you had a stepper and some app and a plotter, right? So we've already covered that in this review. And some information about importing. That really doesn't need it anymore. And what I have here is the general structure of a stepper, repeated. We've already covered this. And a plotter, right? So that first bit of the lecture was just to review the first 3 lectures. And again, here's exactly the same code again. It's just talking about the basic problem of a falling particle and introducing Euler's law yet again, all the way through. So this is already covered. Oh, maybe that one isn't covered. Undo celebration. Okay. The more general problem is when that net force isn't just gravity. Okay, so the complication that we're adding in lecture 4 is we're saying, well, what if the force isn't just the force of gravity, but it's some more complicated force? The general idea is you still have the rate of change of position is equal to velocity. The rate of change of velocity is the net force divided by m. You still apply Euler's method to it exactly the same way. And what we're beginning to recognize is this general pattern that it's this first derivative of some variable equals some function, right? We're trying to abstract this out. So as an example, maybe this net force depends upon gravity, and that force of gravity itself depends upon y. And this was an assignment question, so something to go back to. Another way of thinking about this is maybe the net force depended on the speed. And one way it can depend upon the speed is through a drag force, okay? So a drag force is some force which depends upon how fast you're going. There's 2 ways of modeling drag forces. We can either say the drag force is proportional to the speed, or it's proportional to the square of the speed. And this has to do with the fluid dynamics of the situation. If things are moving very slowly, it tends to be this. If they're moving very quickly, it tends to be this. There's no way for you in this course to know whether or not this or this is the right model. This is part of the physics of the problem. You've got to bring this to the equation before you can solve it, all the way through. But my comment would be that for real world applications, a lot of the things that you interact with, balls being thrown, cars moving, people running, planes flying, it's the second form, which is what we typically talk about as a drag force of an object moving through the air or through water. So that's what this comment says. This idea of saying it depends upon the speed squared and there's a constant of proportionality says that I don't really know what the constant is. This is just whatever number with appropriate units, and coefficients definitely do have units, is needed to multiply a speed squared and get out newtons, right? So meters squared per second squared times something gives you newtons. Whatever you need to put in there to make the units right, that's what C2 has to represent. When and if you take a course in fluid dynamics or continuum mechanics, you'll learn that the structure of this coefficient is really broken up into pieces. This coefficient depends upon a non-dimensional number, the density of the fluid you're going through, the air or the water, and how big the object is. So what we're doing is we're rewriting this one constant in terms of this big constant, 1/2 times CV times rho times AD. C2 represents the coefficient in something times V squared. CD is the drag coefficient. For good or for bad, C2 is called a drag coefficient, and C2 is called a drag coefficient, and CD is also called a drag coefficient. But they're clearly not the same kind of drag coefficient. They have different units. And paying attention to how the question is set up lets you figure out which one it is. Okay, so with that little bit of theory, we want to modify our basic program so that it is solving this equation of motion, one where there is a quadratic dependence on the velocity for the drag. Okay, so let's do that. Let's take all this stuff out, and modify our basic program so that we've got a, where am I here? A falling pebble all the way through. Well, this is the same code yet again. This is the same conversation yet again. This is the same conversation yet again. I don't really need to know what that is. Or Bob, this is just like examples of Python coding. Okay, here we go. Here, falling paper bag. Okay, so here's the example. Let's model a bag, a paper bag, which is light, falling under gravity and having a drag force acting on it, right? So you have a system of equations of motion, right, that we're going to model on this thing. You need to have some basic structure, right? And as we talked about, we're going to have a stepper, some code, which is going to iterate through time, have an optional number of parameters, some initial values, and what it does is it steps through the model. Every time it runs, it returns the current value back to whatever program is calling it. It has an ending condition, calculates the net forces. These are forces as in units of newtons, units of newtons. This is a net force. So to compute the net acceleration, it's the net force divided by m. Okay. We don't really need this last bit to keep it clear, but that's the basic structure of this stepper. We need a plotting program. Here's a plotting program that introduces the idea of multiple subplots, because maybe I want to plot time versus position and time against speed, and some sort of driver program to bring it all together, right? That's the basic pattern. Okay, here we go. Here's the two plots. Position as a function of time, velocity as a function of time. And then if we want to, we could make this interactive, as we did. But for the purposes of these notes, I don't think this interactive bit is overly important. So I'm going to delete that out. Here's the important bit of physics, though. You see that at the beginning it's falling like it would for projectile motion or under constant gravity. But as the force of the drag force increases in magnitude, it reaches a point at which the force of gravity pointing down matches the force of drag pushing up. So you get a net force of 0. So you get no acceleration. So the velocity, which is still negative, still falling, approaches a constant. That is no acceleration. It's approaching what we call a terminal speed, about -3 or so. So the slope of y versus t becomes a constant. That's what that's showing. This last little bit is saying how I could actually read out this number from a data frame. Well, we talked about a data frame, right? The idea that here is one way of looking at the data. If you want to talk about a particular row, you can either talk about the entire row. I guess you can't. A particular row, or you could talk about the last row all the way through. And if you stick in .v or .t or .y, you could get those values out. Okay. Here is another plot experiment where now we're doing it, but we're doing it for several different cross-sectional areas. I'm not sure if this is really needed as something for the course as a big theme. Let's leave it in there. So what this example is doing is it's saying, well, what if there's a parameter like the cross-sectional area, and I want to see how these plots change depending on the cross-sectional area of the object that's falling, a little paper bag versus a big paper bag. So one way I could do that is I could come up with a list of possible parameters and then have an outer loop that loops through all of those possible parameters, run the simulation, and extract out just the terminal velocity, right? take all of these things together and then make a final plot that plots all of the cross-sectional areas against all of the terminal speeds. Okay. The only complication is we're going to now pass in, we want to draw all of these plots on the same set of curves. We don't want to draw a new set of curves every time. So what we're going to do is we're going to bring that subplots command outside of the plot, do it once, and pass it into the paper bag plot so that it can reuse that same set of plots again and again. And this is what we got as a structure. All right, so what you're seeing is depending on the value of A, you get a different terminal velocity. Depending on the cross-sectional area of the bag, you get a terminal velocity. And all this is showing is the cross-sectional area decreases all the way through. So we've now had an example of how you modify a parameter and do a parameter sweep, a sweeping through a program to look at lots of different values. Okay, that's lecture 4. Anything about lecture 4, 1 through 4, that requires more conversation right now? Okay, moving along. By lecture 5, we said, well, things don't just fall straight down. They can move in projectile motion, having a horizontal and a vertical component. So the math was something like this in vector components or in second order differential equations, or you could split it up into different components and use Euler's method. So you just need to recognize that this right here is Euler's method. That's an important idea. What we're doing is we're updating the values of Vx, x, y, and Vy every time step. Because Vx has no net force on it, it never changes. It has no net acceleration. Vy is changing, so it has a change, right? The idea of xi plus 1 is the first time, the second time, the third time, the fourth time. When you're dealing with a force like a drag force, like any force, is a vector. It doesn't point straight up. It points opposite to the direction of velocity. So the notes are, well, if I split this drag force into components, Ft cos theta, Ft sine theta, I can rewrite that so that it's that drag force as a magnitude times the component along a line parallel to velocity. So this is another way of doing it, and we discussed that. So if this analysis is like, I don't get that, I encourage you to grab a piece of scrap paper and just draw it out for yourself. And then we summarize. We say, okay, here's the equation of motion. Now, this set of code is going through in detail what Euler's method is doing. Now, if it was me, I would just delete these two sections because it's redundant. We sort of already covered it. We know how it's all going. I think it was useful as we developed the model, but in terms of study notes, this might be just like too much of extra stuff. I'll leave it in here for now, but if it was me, I would delete these sections all the way through because it's really the same thing again and again. I'll notice that what we're doing is we're introducing a technical term, the idea of coupled or decoupled equations. So what I'll do is I'll make a little note here so we can really see this here. I'll say coupled versus decoupled equations. This is something we introduced as a name. Here, let's be a bit fancier. Let's bold it so we can get that idea. So just as a potential exam question, if I use the word coupled or decoupled, what I mean is, can I solve these equations independently, or do I have to solve them as a group all the way through? X and Y for the classic no air friction problem is uncoupled or decoupled. You can solve X independently from Y. But now, because the velocity or the speed appears in both spots, and the speed depends upon Vx and Vy squared, all these equations are coupled. You have to solve these things all together. Okay, can we take this basic problem right here, and turn that into a standard set of equations? And again, this is the pattern we've been seeing. We need to have a model, some stepper. I call it model, stepper, either one of those words is fine. I need to iterate through it. I need to plot it. That code works just fine. Here's the basic model, right? Now this is a model with no drag forces, right? So this is the basic structure and the plot. There is nothing different about this code versus any of the codes we've seen before. I was trying to emphasize that one of the things you can do is start with a piece of code as a template. Because this code was already done earlier in the notes, here I am going to just delete these sections. It's exactly the same thing that we saw above. So let's just start with a projectile motion app, a generic projectile motion, okay? And what I'm recommending is a strategy on how to write these things, as I've gone over. Start with just running the simplest version of it all the way through. Okay, this is just talking about how to develop that code. I don't think it's needed in the notes. Here is a generic stepper. As before, it passes data back. We're going to explicitly calculate the forces, and then we're going to update the code every which way to do it. In this lecture, I was introducing the idea of test-driven development, making small changes to the code, and then plotting the results. And then we ended the lecture by actually showing you how the whole code worked together. Okay, so I think the cleanest way in terms of your notes to do this is get rid of this version of the code that has the optional piece. That's not important. And just see if this can get to run all the way through.
Yeah, we are, absolutely. I'm just getting
all I'm doing is deleting the parts of the code that are missing. Okay, so here we go. Projectile motion stepper. This is code that actually now implements the drag forces. We need some function that's going to plot the whole thing. And then something that's going to do it. And then we're going to run the program. Oh, and there's an error. G is not defined. Okay, so somewhere in this program, we're going to need to incorporate that parameter G. Let's do it as we've been doing. Just pass it in as a parameter. Okay, so what do we got? We've got a stepper that has this basic pattern. We've got something that plots the results. Here's an example of one where not only do I plot the original solution, but I also plot the analytical solution and then the overall program. G is still not defined. Maybe I didn't run this piece of code. Projectile motion stepper. Oh, G is not defined in the projectile motion plot. Okay, fine. Let's make it a running example. I must have used a global when I did the lecture. Awesome. So what we see is when you have a drag force, right? This is what would happen with the drag force. This is what would happen with no drag force. Without drag, things go a lot further, all the way through. Okay, and then we had another example where we varied the drag coefficient. I don't think that's a useful thing. And this is code that all is going to appear on a future assignment. So let's just eliminate that from the notes. Okay, so what we've developed is the basic structure of a projectile motion with drag, right? So this code bit is a starting point for later codes. And the idea is you should be able to understand what any one part of this is. And one of the things that I've been doing for these tests is basically giving you a code like this and erasing parts of this code and saying, well, what goes in those blanks? That's what I need you to be able to do. Okay, we are done lecture 5. Okay, just checking the time here. I think I get through lecture 6 today, all the way through. Okay, anything about lectures 1 through 5? Hearing nothing, let's continue on. In lecture 6, we add in another dynamical effect. We talked about spinning balls. So when you have a fluid and air or water moving around that body, not only can it exert a drag force, it also can exert a force called a Magnus force, something to do with the spin, okay? The idea of the Magnus force is a spinning object is going to have differential pressures on either side, and the effect of it is going to displace the ball. If the ball is moving from the right towards the left, the Magnus force happens at right angles, perpendicular to the motion of the ball, okay? Why there's a Magnus force is not on this course. All that's on this course is if there is a force which is of this structure, if I give you this, can you solve that system of equations? Okay, so to really break it down is if this is the equations of motion, that's a drag force we talked about, and I tell you this is the Magnus force or this is some force, could you model this system of equations? Okay, so what I could do is I could take this set of notes and really reduce it down. I think it's pretty clear, but this is the basic structure. This is the system of equations. It's getting that much more complicated. Now we've got 3 directions, X, Y, and Z. So you actually have 6 equations. You've got gravity in the Z direction, drag in all 3 directions, and in general, depending on what axis it's spinning around, all the way through. Okay, now I did this problem motivating it for a baseball. It could be for any ball, but here is a generic code which solves this problem. Okay, it's going to step through the code. At every time step, it's going to return back the state of the model. It's going to handle the drag coefficient. Now, when we did this particular problem, baseball drag was something that depended upon some value. So just for the purposes of making this code work, let me just give you sort of a standard drag coefficient. It doesn't even matter what we use. Let's use a drag coefficient like 0.5, right? But in general, depends on the shape of the object and the density of the fluid.
Dr. Munroe,
Yes.
so with that being said, will we be given the drag coefficient should we get a code like this and have to fill
Right.
in
So
the
the
values?
way that would work is the text would say the drag coefficient is given by this expression, and you'd
Okay.
have to put that in.
Okay.
Right. So if we're talking about a smooth ball, then the drag coefficient has the pattern of 1/2 times CD times rho times A squared.
Okay.
But that's only true for a perfect sphere
Yes.
that's smooth. In general, for an object like a baseball, which has that ridge, or a basketball,
Okay.
or any other shape, like a plane, the way you discover what that coefficient is you put it in a wind tunnel and you measure what the drag force is.
Okay.
Right. So for lots of problems, CD might just be a number.
Yeah. So that's
Right.
what I was asking, as in, would we be given CD as a number? Like given the scenario and given CD as a number.
Exactly.
Okay.
It would be in the question what to use there. So the only complication
Okay.
is that this for some objects that might be a number, and for some
Yes.
other objects it might be an expression.
Okay.
1/2 times its area.
Okay. I'm
And
understanding
that depends on the problem. And likewise for the Magnus force. Okay.
Okay.
The Magnus force all the way through here is some number which is determined from experiment. And for some things, if you remember we did the lab on the basketball,
Yes.
you can model what CM should be equal to. You can model that CM should have the form of 16 divided by 3 times pi squared times its area times the density.
Oh,
And
okay.
it's a model, right? But for other
Yes.
objects, you just have to measure it. Okay.
Okay. All right.
Now, as I've written this code, you'll notice the comment says per unit mass and per unit mass. So these values are the drag coefficient when we've already divided by the mass of the object. This is the Magnus force when we've already divided by the mass of the object. So strictly speaking, the units of these things are not newtons. The units are newtons per kilogram. Newtons per kilogram. It's an acceleration. So when it comes to the net equation, it's not really a net force. It's a net force per unit mass. It's really a net acceleration. The reason I bring that up is depending on the formulation of the question. And I will not try and trick you on the final exam. I won't like give you one or the other. But when you're reading these kinds of codes, sometimes when people talk about forces, a force doesn't always mean newtons. It could be force per unit mass. The difference is whether or not you set up the equation like F net is equal to m times g, and then the acceleration is F net divided by m, or do these really represent forces per unit mass? Becomes an acceleration, which means you do not need to divide by m. Another way of thinking about these problems, just to get rid of the complexity, is just assume that the mass is 1 unit, 1 kilogram. It's not a big distinction, and I said for the final exam, I won't try and trick you on choosing one versus the other, but sometimes when reading through this code, there can be a subtlety on, well, is this a force or a force per unit mass? Read the documentation, the comments, think about the units and the values. It's possible that there's a scaling factor of the mass we got to care about. But in terms of an overall code, there's drag coefficients, there's how we would do a Magnus force, and how we would put it all together. So as an application, here is one where we varied the initial angle and then done a visualization showing how a spinning ball depends on how much curve it gives in terms of top spin, side spin, or a long axis spin. And the idea is if you give a ball a bit of a spin, you can make it veer to the left, veer to the right, hit the ground more quickly, hit the ground less quickly, right? And I'm not sure whether or not, oh, look at that. If you give it a spin, it actually will move out to the side as well. And of course, you could, in general, give a ball which had all combination of parameters. Well, that was neat. Sort of went left and then right. Playing around with these things. Again, this interactive thing does not occur on the final exam. It's just to indicate that you can get more complex behavior depending on how you change these parameters. 3D plotting is another way of visualizing this. We're not doing anything on 3D plotting on the final exam, so I'm just going to take it off as a chunk all the way through. Okay, so what we've covered in the last hour and 15 minutes, I said we're doing basically a lecture every 15 minutes. We've covered the first 6, so this is the first third of the course. I think this is a reasonable model for reviewing through the course. So if it sounds good to you, we'll continue this pattern on Monday all the way through. We're going at a pretty good clip, and I think this is appropriate for getting through it. I will add to this document the labs and the assignments, and if there's anything from those that we need to talk about, we can. And the other thing that I've done is, I haven't posted the solutions, but in your folders, you will see a copy of what I used as the final exam last year. you're more than welcome to take a look at this. We may cover it as a class before we get to the end. We might do this as a review session. The only thing I will say about this particular exam is its style is different from what your exam will be. This exam was expected to be done in class in front of a computer. Yours will not be. Yours will be a pen and paper exam. And the other thing is some of the patterns or styles about organizing applications using a stepper and a plotter and an app, I didn't use that set of structure when I taught the course last year. So some of these questions might look a little bit strange, just their setup. So there is how I did this course last year. I had a solver and I allocated arrays, and there's no pandas stuff, and I'm using range. It's the same question, but I didn't use this idea of a plotter and an app. So when you're taking a look at this old final, don't be thrown off too much by the nature of the question. I would ask this in the language that we've been doing our lectures all the way through. But it's something to definitely take a look at as the kind of thing that goes through my brain when I'm thinking about this course all the way through. So it's already posted. I said I'll extract out lectures 1 through 6 and upload that so you can review it. And I think we're at the end of the lecture proper. The lab went pretty quickly on Tuesday. Kyle, did you have any comments about the lab, or was it pretty straightforward?
Pretty straightforward.
It was pretty straightforward, so that shouldn't be a problem. Once you have completed the lab, the last assignment is like that. It's in the flavor of the lab in the sense that it's a kind of collision. It just happens to be a molecular collision. Finish off the lab, take a look at that assignment. But if you'd like to discuss that assignment as a class at some time on Friday, Saturday, Sunday, get in touch with me and we will organize a time, or we could just cover it as a class on Tuesday during lecture, if that would be useful to you. I continued to get through my marking of this course. I've now up to and completed assignment number 3 and uploaded your grades. And one of the things I'll draw your attention to, just to make sure that it's clear that it's there, in terms of what I'm doing, 2820, I don't know, student, let me see if I can see what you see. Right, I'm now a student, I'm pretending I'm a student. So if I go to the grade book, which is what you would see for your grade book, of course, I didn't assign anything here. My assumption, and if this is not happening, please tell me, that when you see your grade, there's some feedback or some note that I have left you for assignment 1 and assignment 2 and assignment 3. Those are comments on your solution that I've given to you that I'm hoping that you are looking at and reading. It says, among other things, where I came up with the grade, but it also might have some suggestions or comments. So take a look at that feedback provided on D2L. If that's not working and you have no idea what I'm talking about, then I'm not clicking the right button. So give me that feedback all the way through, and I'm continuing to work through the marking of these things. Okay. Before I leave the lecture part for today, anything following up? Any last thoughts? Okay, sounds good. You can get through the lab. As again, I'm around. Just flag me on the chat saying, are you available? And I almost for sure will be. And I'll turn on my mic and I'll help you through. But I said from Tuesdays, Kyle, I think only one person asked me one question. Kyle, I'm sure, has got it totally under control. But as before, if there's anything else I can do to help, just please let me know and I'll try and accommodate. Okay, thanks very much. Talk to you later.